Good morning, everyone. Welcome to the second lecture of this NLP series. Today's lecture is going to be on Ngram language models. I am Arghya Kundu, and my email ID is arghyak@yourq.ca. If you have any questions, please feel free to drop me an email. In today's lecture, we are going to cover these 4 chapters. The first is the introduction to Ngrams. The second is the estimating Ngram probabilities. The third is evaluation of the language models and the perplexity. And finally, we're going to talk about generalization and zeros. So let's get started with the first topic in today's lecture, that is the introduction to Ngrams. "You are uniformly charming," he cried, with a smile of associating. Now, many of you might think that this is a sentence took out from a book or something, but rather this is a sentence that was generated by a Jane Augustine bigram model, which is a random sentence generator. So the NLP models, the prediction models are very, very powerful nowadays. Even with one of the most simplest models like the Ngrams. Predicting is difficult, especially about the future, as the old quip goes. But however, predicting something that seems much easier, like the next few words someone is going to say. What word, for example, is likely to follow, like, "Please turn your homework"? Hopefully, most of you concluded that a very likely word is "in" or possibly "over," rather than "mobile" or "ball." In the following sections, we will formalize this intuition by introducing models that assign a probability to each possible next word. The same models will also serve to assign a probability to an entire sentence. Such a model, for example, could predict that the following sequence has a much higher probability of appearing in a text. That is, "All of a sudden I noticed 3 guys standing on the sidewalk." This sentence is much more has higher probability of appearing in a book or sentence or a text than the jumbled up words of the same sequence. Why would you want to predict upcoming words or assign probabilities to sentences? Right? That is the main question. So probabilities are essential in any task in which we have to identify words in noisy, ambiguous input, like speech recognition. For example, for speech recognition, it is easier to realize that you said, "I saw a van," rather than "I saw of an." So the probability of that "I saw a van" is much more higher than the second probability of the different sentence. The same goes for spell correction. In a spell correction model, the probability that about 15 minutes from is much more higher than the same sentence which with the minutes word spelled wrong. Now, another interesting area in which the probabilistic language models are used is machine translation. So for example, the probability of, suppose you're translating something from Chinese to English, and in the Chinese sentence it says that "high winds tonight," right? So it's the probability of this sentence, that's "high winds tonight," is much more higher than "large winds tonight." So this is where the language models comes into play. So for example, automatically translating from any languages, Chinese or Spanish to English, or even Spanish to Chinese or Chinese to Spanish, the probability of the words of the sentence that has a similar meaning to the sentence belonging to the primary language, that is a language from which we are translating, is much more higher than any other sentence that can refer to the original sentence. Probabilities are also important for augmentative and augmentative communication systems. People often use such augmentative and augmentative communication systems devices in which they are physically unable to speak or sign, but can instead use eye gaze or other specific movements to select words from a menu to be spoken by the system. What prediction can be used to suggest likely words from the menu? Models that assign probabilities to sequences of words are called language models. So the goal is to compute the probability of an entire sentence or a sequence of words. So mathematically, we can represent this as the first equation here, that is P of W. That is, the W means the entire sentence, which consists of the words 1 to n in that sequence. So the P of W represents the probability of that sentence, how much likely that sentence is to appear, or how likely that sentence can appear in a text. And a related or a subtask can also be predicting the upcoming word. So that can be formally stated with the second equation, that is the probability of 5, the fifth word in that sentence, the probability that that particular word will appear, given that the last 4 words was from word 1 to word 4. A model that computes either of this is called a language model, or a LM. In this lecture, we'll introduce the simplest model that assigns probabilities to sentences and sequences of words, the n-gram model. An n-gram is a sequence of n words. A 2-gram, also called a bigram, is a 2-word sequence of words like please turn your, or your homework. And a 3-gram, also called a trigram, is a 3-word sequence of words like please turn your, or turn your homework. We'll see how to use n-gram models to estimate the probabilities of the last word of an n-gram given the previous words, just like the equation I showed you earlier. And also to assign probabilities to entire sequences, which is represented by the first equation. In a bit of terminological ambiguity, we usually drop the word model and use the term n-gram or bigram or trigram to mean either of the word sequence itself or the predictive model that assigns it a probability. While n-gram models are much simpler than the state-of-the-art neural language models based on the RNNs and transformers that we will discuss in other lectures, however, the n-gram models are very important as they are the foundational tools for understanding the fundamental concepts of language modeling. So let's begin the task of computing the probability of P, W given H. The probability of a word W given some history H. Suppose the history H is its water is so transparent that, and we want to know the probability that the next word is the. So this can be written as the probability of the given its water is so transparent that. One way to estimate this probability is from relative frequency counts. Take a very large corpus. count the number of times we see its water is so transparent that, and count the number of times it is followed by the. This would be answering the question, out of the times we saw the history H, how many times was it followed by the word W? And it can be represented by the equation in the screen. With a large enough corpus, such as the web, we can compute these counts and estimate the probability from this equation. You should now pause the video, go to the web and compute this estimate for yourself. While this method of estimating probabilities directly from counts works fine in many cases, it turns out that even the web isn't big enough to give us good estimates in most cases. This is because language is creative. New sentences are created all the time, and we won't always be able to count entire sentences. Even simple extensions of the example sentence may have counts of 0 on the web. Similarly, if we want to know the joint probability of an entire sequence of words like its water is so transparent, we could do it by asking, out of all possible sequences of 5 words, how many of them are its water is so transparent? We would have to get the count of its water is so transparent and divide it by the sum of the counts of all possible 5-word sequences. And yes, that seems rather a lot to estimate. For this reason, we'll introduce more clever ways of estimating the probability of a word W given an history H. This is where the chain rule comes into play. Now, if you recall the definition of the conditional probabilities, that is, the probability of B given A is equal to the probability of A and B, that is the joint probability of A and B, divided by the probability of A. We can rewrite this equation as the probability of A and B is equal to the probability of A multiplied the probability of B given A. So this can be extended as a chain rule as shown in the last equation of n random variables. The chain rule shows the link between computing the joint probability of a sequence and computing the conditional probability of a word given previous words. The equation shown suggests that we could estimate the joint probability of an entire sequence of words by multiplying together a number of conditional probabilities. For example, the probability of its water is so transparent, the probability of this entire sentence is equivalent to the probability of its multiplied by the probability of water given its multiplied by the probability of is given the previous 2 words where it's water, and so on. However, as you can rightly imagine, using the chain rule doesn't really seem to help us because we don't know any way to compute the exact probability of a word given a long sequence of preceding words. As I said before, we can't just estimate by counting the number of times every word occurs following a very long string, because language is creative and any particular context might have never occurred before. The intuition of n-gram model is that instead of computing the probability of a word given its entire history, we can approximate the history by just the last few words. The bigram model, for example, approximates the probability of a word given all the previous words by using only the conditional probability of the preceding word. In other words, instead of computing the probability of the given its water is so transparent that, we can just calculate the probability of the given that is the number of times the occurs after the word that in the entire text corpus. And also we can extend this to a trigram model. For example, this probability can also be computed in a trigram model, for example, with by using the equation of by calculating the probability of the given the last two words were transparent that, total number of times that occurs. So the bigram model is much more better than the unigram model. However, it is less accurate than the trigram model. So as I said before, we can extend this to trigrams, 4grams, and 5grams. In general, this is an insufficient model of language because language has long distance dependencies. That is, a word that has occurred, say 6 or 7 words before, might have some dependency with the word that is at the present, at the very end. So in general, 5grams are much more better, are much more accurate than 4grams. 4grams are much more accurate than trigrams. But anyway, we can often get away with n-gram models. Now, how do we estimate this bigram or n-gram probabilities? An intuitive way to estimate the probabilities is called the maximum likelihood estimation, or the MLE. Excuse me. We get the MLE estimate for the parameters of an n-gram model by getting counts from a corpus and normalizing those counts so that they lie between 0 and 1. For example, to compute a particular bigram probability of a word Wn, given a previous word, say Wn-1, we will compute the count of the bigram Cwn-1 Wn and normalize it by the sum of all the bigrams that share the same first word, that is Wn-1, as provided by the first equation. Now, we can simplify this equation since the sum of all bigram counts that start with a given word Wn-1 must be equal to the unigram count of that word Wn-1. Right. So I hope you get this, because the count of a given word Wn-1 must be equal to the unigram count of that particular word Wn-1. So this can be written as the second equation. Now let's work through an example using a mini corpus of 3 sentences. However, first we need to augment each sentence with a special symbol S at the beginning of the sentence to give us the bigram context of the first word. We will also need a special symbol at the end as provided in the example. Now, let's look at the calculations. So the bigram probabilities for this corpus, that is a probability of I occurring before the beginning character, is 2 by 3, that is 0.67, right? And for example, the bigram probability of Sam appearing after M is 1 by 2, that is 0.5. Because as you can see, the total number of Sam, the word Sam appearing before M is 1, that is in the first sentence. And the total number of M's appearing in these 3 sentences are 2, that is it is located in the first sentence as well as in the second sentence. So the probability is 1 by 2, that is 0.5. Now let's move on to some examples from a slightly larger corpus than the 14 word example that I showed before. For this, we will use the data from a now defunct Berkeley restaurant project. This was a dialogue system from the last century that answered questions about a database of restaurants in Berkeley, California. So as you can see, the sum of the text normalized sample user queries are shown in the slide. So this figure shows the bigram count for a piece of bigram grammar from the Berkeley restaurant project. Note that the majority of the values are 0. In fact, we have chosen the sample words to cohere with each other. A matrix selected from a random set of 7 words would be even more sparse. The next table shows the bigram probabilities after normalization, that is dividing each cell in the previous figure by the appropriate unigram probability unigram for its row taken from the first table in the slide. So as you can see, the bigram probability of I occurring after of I of want occurring after I, that is the sentence I want, is 0.33. And the probability of, say, food occurring after want, say suppose want food, right? So that is 0.0065. Now, we can compute the probabilities of sentences like I want English food or I want Chinese food by simply multiplying the appropriate bigram probabilities together. For example, the probability of I want English food, it can be translated as the probability of I given the previous word is the beginning of the sentence multiplied by the probability of want given the previous word is I, and so on and so forth. So using the previous table shown here, we can get these values, and the multiplied value of that is the probability of the sentence that's I want English food. The entire probability of this sentence is 0.00031. Now you can use the same table before, as I showed before, to compute a slightly different probability of, say, suppose I want Chinese food, right? So this is the probabilities that I shown you. Now, what kind of linguistic phenomena are captured in this bigram statistics? Some of the bigram probabilities above encode some facts that we think of as slightly syntactic in nature, like the fact that what comes after it is usually a noun or an adjective, or that what comes after to is usually a verb. Others might be a fact about the personal assistant task, like the high probability of sentences beginning with the words I. And some might even be the cultural rather than linguistic, like the higher the probability of people are looking for Chinese versus English food, right? Now let's get into some practical issues. Although I have talked about bigram models, in practice it's more common to use trigram models, which condition on the previous two words rather than the previous word, or 4-gram models, or even 5-gram models, which when there is a sufficient amount of training data. Now note that for these larger n-grams, we'll need to assume extra context to the left and right of each sentence end. For example, to compute trigram probabilities at the very beginning of the sentence, we use 2 pseudo words for the first trigram. We always represent and compute language model probabilities in log format as log probabilities. Since probability is by definition less than or equal to 1, the more the probabilities we multiply together, the smaller the product becomes, right? So multiplying enough n-grams together would result in a numerical underflow. By using log probabilities instead of raw probabilities, we get numbers that are not as small. Adding in log space is equivalent to multiplying in linear scale. So we can combine log probabilities by adding them. The result of doing all computations and storage in log space is what we only need to convert back into probabilities if we need to report them at the end. Then we can just take the exponential of the log probabilities, right? Now, some of the most popular language modeling toolkits are SRI-LM and KEN-LM. So these are publicly available toolkits for building an n-gram language model, and you can find them in the links provided here. By using a text from the web or other enormous collections, it is possible to build extremely large language models. The Web 1 trillion 5-gram corpus released by Google includes various large datasets of n-grams, including 1 gram through 5 grams, from all the 5-word sequences that appear in at least 40 distinct books, from publicly accessible web pages in English. Google has also released Google Books n-grams corpora with n-grams drawn from their book collections, including another 800 billion tokens of n-grams from Chinese, English, French, and German. Smaller but more carefully curated n-gram corpora for English includes the million most frequent n-grams drawn from COCA, that is the corpus of contemporary English American language. 1 billion word corpus of American English COCA is a balanced corpus, meaning that it has roughly equal numbers of words from different genres: web, newspapers, spoken conversation, transcripts, fiction, and so on, drawn from the period between 1990 to 2019, and has the context of each n-gram as well as labels for genre and provenance. Some examples of 4 grams from the Google Web Corpus is shown here. Now, efficiency considerations are important when building language models that use such large sets of n-grams. Rather than storing each word as a string, it is generally represented in memory as a 64-bit hash number, with the words themselves stored on disk. Probabilities are generally quantized using only 4 to 8 bits, and n-grams are stored in reverse drive. An n-gram language model can also be shrunk by pruning. For example, only storing n-grams which counts greater than some threshold, or using entropy to prune less important n-grams. Another option is to build approximate language models using techniques like Bloom filters. This is a link where you can find the Google n-grams corpus. Now let's talk about evaluation and perplexity. The best way to evaluate the performance of a language model is to embed it in an application and measure how much the application improves. Such end-to-end evaluation is called extrinsic evaluation. Extrinsic evaluation is the only way to know if a particular improvement in a component is really going to help the task at hand. Thus, for speech recognition, we can compare the performance of 2 language models by running the speech recognition system twice, once with each language model, and seeing which gives the more accurate transcription. Unfortunately, running big NLP systems end-to-end is very expensive. Instead, it would be nice to have a metric that can be used to quickly evaluate potential improvements in the language model. An an intrinsic evaluation metric is one that measures the quality of a model independent of an application. For an intrinsic evaluation of a language model, we need a test set. As with many of the statistical models in our field, the probabilities of an n-gram model come from the corpus that is trained on, that is the training set or the training corpus. We can then measure the quality of an n-gram model by its performance on some unseen data called the test set or the test corpus. So, if we are given a corpus of text and want to compare two different n-gram models, we firstly divide the data into training and test sets, train the parameters for both of the models on the training set, and then compare how well the two trained models fit the test set. But what does it mean to fit the test set? The answer is simple. Whichever models assigns a higher probability to the test set, meaning it more accurately predicts the test set, it is a better model. Given two probabilistic models, the better model is the one that has a higher fit to the test set. Or the beta predicts or that beta predicts the details of a test set, and hence will assign a higher probability to the test set data. Since our evaluation metric is based on test set probability, it is important not to let the test sentences into the training set. Suppose we are trying to compute the probability of a particular test sentence. If our test sentence is part of the training corpus, we will mistakenly assign it an artificial high probability when it occurs in the test set. We call this situation training on the test set. Training on the test set introduces a bias that makes the probabilities all look too high and causes huge inaccuracies in perplexity, the probability metric that I'll discuss later. Sometimes we use a particular test set so often that we implicitly tune to its characteristics. We then need a fresh test set that is truly unseen. In such cases, we call the initial test set as the development test or the dev set. How do we divide our data into training, development, and test sets? Well, we want our test set to be as large as possible since a small test set may be accidentally unrepresentative. But we also want as much training as possible. At the minimum, we would want to pick the smallest test set that gives us enough statistical power to measure a statistically significant difference between two potential models. In practice, we often just divide our data into 80 training, 10% development, and 10% test set. So given a large corpus that we want to divide into training and test data can either be taken from some continuous sequence of text into the corpus, or we can remove smaller strips of text from randomly selected parts of the corpus and combine them into a test set. Now, as I said, the extrinsic evaluation is very time consuming and it can even take up to weeks. So sometimes we use intrinsic evaluation to compare the two models. However, it must be noted that even if a model has a better intrinsic evaluation, it does not mean that it is the perfect fit. In practical purpose, to check whether a model is good or not, we should always have to do the extrinsic evaluation at one point of time. So that's why generally we use intrinsic evaluation in pilot experiments. Now, what is perplexity? Well, in practice, we don't use raw probabilities as our metric for evaluating language models, but a variant called perplexity. The perplexity of a language model on a test set is the inverse probability of the test set, normalized by the number of words. For a test set W, which has 1 to n words, the perplexity is defined by the first equation. We can also use a chain rule to expand the probability of W, as shown in the next equation. Thus, if we are computing the perplexity of W with the bigram model, we get the one that is shown in the last equation. Now note that because of the inverse of this equation, the higher the conditional probability of a word sequence, the lower is the perplexity. Thus, minimizing perplexity is equivalent to maximizing the test set probability according to the language model. What we generally use for word sequence is the entire sentence of word in some test set. Since this sequence will cross many sentence boundaries, we need to include the begin and end markers in the probability computation. We also need to include the end of sentence marker in the total count of word tokens. There is another way to think about perplexity as the weighted average branching factor of a language. The branching factor of a language is the number of possible next words that can follow any word. Consider the task of reorganizing the digits in English, 0 to 9. Given that each of the 10 digits occur with probability p is equal to 1 by 10. The perplexity of this mini language is in fact 10. To see that, imagine a test string of digits of length n and assume that in the training set all the digits occurred with equal probability. Thus, by the previous equation, the perplexity will be 10, as shown in this equation. But suppose that the number 0 is really frequent and occurs far more often than other numbers. Let's say that 0 occurs 91 times in the training set and each of the other digits occur 1 time each. Now we see that the following test set says 0, 0, then 3 times 0, then 1, 3, and the rest 4 zeros. We should expect the perplexity of this test set to be lower since most of the time the next number will be 0, which is very predictable. That is, has higher probability. Thus, although the branching factor is still 10, the perplexity or the weighted branching factor is smaller. Finally, let's look at an example of how perplexity can be used to compare different n-gram models. We trained n-gram, bigram, and trigram models on 38 million words from the Wall Street Journal using a 19,979 word vocabulary. Then we computed the perplexity of each of these models on a test set of 1.5 million words. The table shown here gives a perplexity of 1.5 million words in the test set. So as you can see, the more information the n-gram gives us about the word sequence, the lower is the perplexity. Note that in computing perplexity, the n-gram model P must be constructed without any knowledge of the test set or any prior knowledge of the vocabulary of the test set. Any kind of knowledge of the test set can cause perplexity to be artificially low. The perplexity of two language models is only comparable if they use identical vocabularies. An improvement of perplexity does not guarantee an extrinsic improvement of the performance of the language processing tasks like speech recognition or machine translation. Now let's talk about generalization and zeros. The n-gram model, like many statistical models, is dependent on the training corpus. One implication of this is that the probabilities often encode specific facts about a given training corpus. Another implication is that the n-grams do a better and better job of modeling the training corpus as we increase the value of n. We can use the sampling methods from the previously learned lectures to visualize both of these facts. To give an intuition of the increasing power of higher order n-grams, this figure shows the random sentences generated from unigram, bigram, trigram, and 4-gram models trained on Shakespeare's work. The longer the context on which we train the model, the more coherent the sentences are. In the unigram sentences, there is no coherent relation between words of any sentence for a final punctuation. The bigram sentences have some local word-to-word coherence, especially if we consider the punctuation counts as a word. The trigram and 4-gram sentences are beginning to look a lot like Shakespeare. Indeed, a careful investigation of the 4-gram sentences shows that they look a little too much like Shakespeare. The words that "it cannot be but so" are directly from King John. This is because, not to put the knock on Shakespeare, his ovary is not very large as corpora. Go. And our n-gram probability matrices are ridiculously sparse. There are this many possible bigrams alone, and the number of possible 4-grams is shown in here. Thus, one of the generator has chosen the first 4-gram, "it cannot be but." There are only 5 possible continuations. That is that, I, he, though, and so. Indeed, for many 4-grams, there is only one continuation. To get an idea of the dependence of a grammar on its training set, let's look at an n-gram grammar trained on a completely different corpus. The Wall Street Journal newspaper, Shakespeare, and the Wall Street Journal are both English, so we might expect some overlap between our n-grams for the two genres. This figure shows sentences generated by unigram, bigram, and trigram grammars, trained on 40 million words from the WSJ. Now compare these examples with the pseudo Shakespeare in the previous figure. While they both model English-like sentences, there is clearly no overlap in generated sentences, and little overlap even in small phrases. Statistical models are likely to be pretty useless as predictors if the training set and the test sets are different, as Shakespeare and the WSG. So how do you deal with this problem when you build n-gram models? One step is to be sure to use a training corpus that has the similar genre to whatever task we are trying to accomplish. To build a language model for translating legal documents, we need a training corpus for legal documents. To build a language model for a question answering system, we need a training corpus of questions. It is equally important to get training data in the appropriate dialect or the variety, especially when processing social media posts or spoken transcripts. Now, what are the perils of overfitting? The n-grams only work well for word predictions if the test corpus looks like the training corpus. Well, in real life, it doesn't often happen. Also, we need to train robust models that generalize. That is, we need to train on corpus that have different genres. One kind of generalization is the zeros, things that don't ever occur in the training set, but they do occur in the test set. Our models may still be subject to the problem of sparsity. For any n-gram that occurred a sufficient number of times, we might have a good estimate of its probability. But because any corpus is limited, some perfectly acceptable English word sentences are bound to be missing from it. That is, we'll have many cases of putative zero probability n-gram that should really have some non-zero probability. Consider the word probabilities as shown, with bigram denied the WHG tree bank 3 corpus together with the word counts. Our model will incorrectly estimate the probability of offer given that denied the is the previous one is as 0. These zeros, things that don't even occur in the training set but do occur in the test set, are a problem for two reasons. First, their presence means that we are underestimating the probability of all sorts of words that might occur, which will hurt the performance of any application we want to run on this data. Second, if the probability of any word in the test set is 0, the entire probability of the test set is 0. By definition, perplexity is based on the inverse probability of the test set. Thus, if some words have 0 probability, we can't compute perplexity at all, since we cannot divide by 0.